All right, this is video 627. It is a last kind of section. It's actually the last three sections, 6.4 to 6.6, and it's about optimization. So this is real life stuff. It's about calculating maximum minimums, and think about if you have a business, you maybe want to be able to figure out how to get the maximum profits, minimum costs, trying to figure out how to balance the two of them. Okay, two things. Spoiler alert. Sorry, this way. When you're done your graphing, the maximum minimums always occur at the corners of the feasible area. You don't have to look for them. They're just where lines intersect. And honestly, most of the time, you can reason out the maximum and minimums when you want to check your work. So even if you're not 100% sure what we're looking at right now, let's dive into a question and we'll go through it slowly and it should clear it all up for you. All right, try again. A toy manufacturer makes two types of toy vehicles, racing cars and sport utility vehicles. Because the supply of materials is limited, no more than 40 racing cars and 60 SUVs can be made each day. Okay, so I'm sensing there's an inequality happening here and something there. However, the company can make 70 or more vehicles in total every day. So I'm seeing the or more. So that's got something else to do with an inequality. There are many possible combinations of racing cars and SUVs that could be made. The company wants to know the combinations that will result in the minimum and maximum costs and what those costs will be. All right, so, and here's the set of questions that you do for like every optimization type question. Right. What does the company want to optimize? And optimize is a fancy word to say, what do they want to minimize and maximize? And in this case, it's the cost. Right, so it says right there. All right, what is going to determine the maximum or minimums? Define these variables and identify any restrictions on them. Okay, so what determines how much they spend? Well, it depends on what kind of cars they make. So it's going to be the number. Let's see. We'll go R for now. It's number of racing cars. Made. And S is the number of SUVs made. Now, restrictions, let's see. On my racing car, okay, not more than 40 per day. And also, what kind of numbers would that be? Well, it's not real, it's not integers. It doesn't say they have to make one every day. So I'm going to say it's whole numbers. Now SUVs, not, sorry, you guys can barely see what I'm doing. More than 60 per day. Oopsie, 60 per day. And I'm also going to choose whole numbers there. If you're not sure what to choose when you've got a word problem, just use whole numbers. It's the one that's most going to make the most sense. Write the system of linear equalities to describe all the constraints on the system. All right, so R has to be less than or equal to 40. Right, not more than 40 a day. So 40 is still okay. And S is less than or equal to 60. And it says in total, the company can make, so if I take my racing cars plus my SUVs, it should be bigger than or equal to 70. So here's the weird part. The whole thing about the money, what we're going to maximize or minimize, actually isn't part of our linear system. That's going to show up later. We want to just see how much they can make. And once we know that, then we can calculate out the prices. Now, this is a lovely video that has 2 pages. All right, so let's look at here. So the next thing you would do is draft the system, and you're welcome, because I already drafted it for you. Okay, so here we've got, and this was nice, I stole it from the textbook. This is your SUVs across here. This is your number of racing cars. And you can see where you've got your overlap. So, excuse me, racing car is less than or equal to 40. So, racing cars. Your SUVs is S is less than or equal to 60. So that's this way. And then the angled line, going this way, is R plus S is greater than or equal to 70, which are the ones we had. Unlike most of the time where I switched to X and Y, I knew this graph had R's and S's, so I just left it the way it is. So we graph our system, and our feasible unit, our feasible spot here, is this one. Now, the objective function, which represents the relationship between the variables and the quantity to be optimized. So cost is equal to, all right, it says it costs $8 to make a racing car. So 8 racers plus makes, I'm pointing and you can't see, but it's the question, 12 SUVs. All right. So here's the spoiler. The textbook expects you to go through a bunch of options and figure it out yourself, but use the objective function to determine the max and minimum by using our corners. So, well, I guess I don't need to number them. So 30 and 40. Now the 30, this is my SUVs. I want to have X's and Y's in there, and that's my R's. So cost is equal to 8 times 40, whoopsies, plus 12, oops, what's my sports, times 30. So cost is equal to 240 plus 12 times 3, 360. I want to say that's 500, but it's probably not. It's probably 600. Anyway, 240, oopsies, plus 360. All right. So this one, $600. Let's try this one, 60 and 10. So cost, and this is S and this is R, 8 times 10 plus 12 times the SUVs. Oops, keep doing that. And I want 60. It's going to be 80, 12 times 6, 720. Whoops, I said 720, I forgot to write it. So the cost, if you add that up, that's going to be 800. And last one is 60 and 40. And this is my S and this is my R. Oh, you couldn't see what I was doing. So my cost is equal to 8 times my 40 plus 12 times 60. 8 times 40 is 320 plus 12 times 60, oh, that's 720. Okay, so this is the minimum, and this is maximum. So that is the minimum cost and the maximum cost. But you know, we can kind of think this one out, at least for the max. Okay, so you can see if my answer is reasonable. Okay, the things we know. We can't make 40 racing for $8. I'm gonna make up to 60 SUVs for $12. And basically we must make 70 or more. Right? That's just from the question. So if you want to make minimum costs, yeah, this is just logicking it through, but it should support. So what you want to do is you want to make as many of the cheap ones as you can. As possible. Okay. And let's see, so as cheap as possible and just enough more expensive ones. So cheap ones are the racing cars. So you want to make 40 racers for $8 each. Now, that's going to be $320. No. Oh, I did my math wrong over here. Oopsies. You guys yelling at me? Should have been 320. Plus 360, that's going to give me 680. All right. That's $320 for that. Yeah, it says we have to make at least 70 per day. So if we've made 40, that means we have to make 30 more of these expensive ones. So 30 SUVs at 12, and 3 times 12 is like 360, which gives you the same thing that we got right there. Max cost. Well, since the question says you can make 70 or more, you can make as many as you can. As possible. So I'm going to make 40 racers at $8 a piece, and I'm going to I can make up to 60 SUVs at $12 a piece. 40 times that is 320, and that's 720, 1040, and there you go. There's your maximum amount. So for a question like this, we can figure out the maximum and minimum without doing the graph, but the moment you get more things involved, or it's not so easy to reason out, you need to use your graph. So remember, you graph it like you would any other system, and then when you're looking to optimize, you look on the corners. It's going to be, your max is going to be one corner, your minimum is going to be one corner. Okay. And I guess there'll be one in the middle if there's 3 corners. All right, and that is the end of the video. Thanks.